inverses. The next important topic in basic linear algebra is eigenvalues and eigenvectors. Okay. Before we proceed, we'll go back to matrix inverses again, right? Let's say we have a vector in Rn, okay, and this is usually an n vector like this, right? But whenever a vector is usually a geometric quantity, right? It's some arrow in some space, right? But whenever we put down numbers for a vector, right, for a geometric entity, for example, let's say this is R2 that I'm interested in. I've chosen this as my origin. If I say I'm interested in this point, right, and I can think of this point as this arrow starting from my arbitrarily defined origin. Okay. This point in space is this point, right? But how we numerically represent this changes depending on the basis that you use, right? If I use these two as my basis vectors, this has some represents. You'll use a couple of you'll get a couple of numbers that represent this vector in terms of these two vectors. If somebody else uses these two basis vectors, then they'll have a completely different representation. So we know that the numerical representation of a vector is basis dependent. Okay, so this is basis dependent, and whenever somebody does not say anything about what basis they are representing the vector in, we assume that it's in the standard basis. Okay. Now, let's say this is x. Let's actually take R2, right? Let's say I have an x vector like this. Since I have not said what basis this is represented in, you assume that it's in the standard basis. Now let's say I have another basis like this. Okay. I call this, let's say, the A basis. Okay. How do I find the representation of this vector x in the A basis? How do I go about finding that out? Matrix inverses, right? How do I find out? What is the procedure I need to follow to find out the representation of x in the A basis? And I'll call this A1, A2. Okay. A1 into x, is it? So you take the vector A1, you take the vector A1 and then multiply it by x like this. A1 transpose. Yes, so we need to find out alpha. That's correct. Should produce my 2, 1. That means the question is, how do we find alpha 1, alpha 2? Given that we know x, we know A1, A2. Yes, that's all. See here, this is nothing but A1, A2 multiplied by this vector alpha, which is equal to x. I know A, I know x, I can solve for alpha. So in fact, if I want to find the representation of vector x in the A basis, all I have to do is first form this matrix A whose columns contain the basis vectors. And then if I take the inverse of this, and multiply it by x, then I will get my alpha, the representation of x in the A basis. The convention we will follow is, because this is the representation of x in the A basis, we will usually write it as, so this is x in the A basis, and you obtain it from x by A inverse. So the inverse of a matrix is really a basis changing operation. Whenever you see an inverse, one way to interpret that inverse is you're changing basis. Basis change. Okay. You can tell me what xa is for this. You can solve it and tell me what is xa in this case. We know what x is. What is xa? Yeah, you have it? Yeah. I don't know. Can you verify? How will you verify? Yeah, substitute it and tell me. If it comes out to be equal, then you're right. Yeah, it's okay. So yeah, so in the standard basis, this vector is to 1, but in this arbitrary basis that we've chosen, A1, A2, the corresponding representation of the same geometric entity, for example, this is the origin, this point, or the arrow representing this point, or this point in space, if you're using the standard basis, I would convey information about that point using these two numbers. If you're working in the A basis, then we would use this. But the underlying reality is the same. We are both of us are talking about this point. It's just that our references are different. Okay, before we proceed, right? I conveniently said take A inverse. But how do I know A inverse exists to change basis? In fact, we don't even know if this is square, right? So, when does the inverse of a matrix exist? When do you have an inverse for a matrix A? What are the conditions? No, that's what A inverse does. What is the condition on A for A inverse to exist? We've not discussed determinants, we've discussed something else. So can we full rank and the more fundamental one? Square and full rank, right? Here I've conveniently said, okay, AXA equals x, and I said just take the inverse of A. How do I know A inverse exists? It's square, or is it square? If you're talking about why is it square? Why is it square and why is it full rank? Okay, the columns of A form a basis for Rn, so what? Yes. Yep, and how many are there? If it's from Rn, no Rn. There'll be n. Yeah, so it will in fact be a square full rank matrix because the columns form a basis for Rn. So this always exists if the columns are a basis for the space that you're interested in. Okay. Right. So this is about vectors and their representation. Right. see, when we talk about matrices, right, we know these in general. So for example, this is a P cross Q matrix, then this is a mapping from what to what? What space to what space? If this is a P cross Q matrix. Yes, this is from RQ to RP. And these represent, in fact, linear transformation, right? In fact, every possible linear transformation from RQ to RP is represented by the set of all P cross Q matrices. Okay, and because we always attach a geometric notion to concepts that we discuss in linear algebra. We said vectors are, n vectors like this are arrows like this. And linear or any transformation from RQ to RP is essentially a process of taking a vector in RQ and then transforming it to another vector in RP. Right? Because you take some vector x and then this is some vector x and this is x. X is a q vector, ax is a p vector. But so geometrically you can think of this linear transformation or any transformation for that matter as simply taking a vector from RQ and then performing some geometric operation and getting another vector in RP. Okay. And in general, when we are talking about linear transformations, right? Linear transformations perform three geometric operations. Geometric operations on vectors. Okay. For now, we will restrict ourselves to only square matrices. RP to RP. Okay. In general, if you are talking about square matrices that transform, take vectors from RP and produce another vector in RP, they perform scaling. So they stretch or compress vectors. Matrices in general will rotate vectors in space. Okay. And they will also, or they can also, see, in fact, a matrix could do all of them or just some of them. Okay. It could scale, rotate or reflect. Okay. And we'll see examples of each of those. And we'll restrict ourselves to R2 for now. Right. Let's say we are talking about matrix like this. Yeah, I'll come to that. Okay. We will use blue for the input space and maybe orange for the output space. Okay. I mean, we have this matrix. If I give you a vector, you will immediately tell me what Ax is. That's easy to do. Okay. But we want to understand what geometric operation is being performed by this matrix. Okay. Let's say we choose a vector. We choose this vector. Let's say it's 2, 1. Is it still visible? Okay. It's 2, 1. So A simply takes 2, 1 and what does it produce? Just multiply it out and tell me what the new vector is. Two comma 2 is it? 4 comma 2. So that's 4. But if I have this, -1, -1. Yeah, so it will simply be in fact, if you put any vector x here, what do you get? Sorry, 2 times x, right? So this is an example of a matrix that only scales vectors. Okay, it does not rotate them. For example, if you superimpose these two, right? These two vectors will lie on the same line. Okay, it's just they are scaled. Similarly, these two vectors will lie on the same line. In fact, if you take any vector, the resulting vector will be along the same direction as the original vector. It will just be scaled by a certain amount. What about this? I'm going to draw it in the same graph. I'm not going to separate now. Let's say 2, 1 again. Sorry. No, write down. Only scales? No, write it down. Yeah. 2, 1, 1 minus 1. Four, 1, is it? Okay. Let's see. Okay, what about 1 minus 1? What is it? -2, 1. Okay. What is this doing? Is it scaling the vectors? Changing their lengths? Yeah, it's changing its length. But it's also rotating them. Right? So for this one, for example, this matrix took this vector, stretched it out, and then rotated the vector to get this. Similarly, it took this vector, stretched it out, and then rotated. And the rotation seems to be different for different vectors. For example, this was rotated in the clockwise direction, whereas this was rotated in the counterclockwise, or if you want to say, okay, it was rotated by counter or clockwise direction as well. My point still holds. The angle by which the vector was rotated was different. So this seems to be scaling the vector and rotating each vector by a different amount. And it's possible the scaling is also different for different vectors. You can verify that later on. Compare the lengths of these two and compare the lengths of these two. Okay, so this is an example of a matrix that scales and rotates. Okay. Yeah, what about this one? Same, 2, 1, 1 minus 1. 3 by root 2, 1 by root 2. Is that right? For this? For 2, 1? Okay. What is 3 by root 2? You'll have to use a calculator and roughly tell me. It's 3 divided by, it's about 2. Okay. Maybe slightly greater than 2. No, will be rotated. Hey, hold on. Is that so? 3 by root 2. It's about greater than 2, is it? Okay, is that right? 2.12 is it? Okay. It's somewhere here. Why? 1 by root 2 is it? It's 0.7. Okay. So it's maybe somewhere here. What about 1 minus 1? 0 minus 2 by root 2 is it? It's just root 2, right? Minus root 2. 0 minus root 2. Hey, hold on. That does not sound right. Is that right? No. What is going on? It's fine. That's weird. Hey, is it minus 2 by root 2 or plus 2 by root 2? Is it minus? Why is it minus? So it's minus 1, 1. This is weird. Okay, let's do one thing. I'm not able to see it. What will happen if you multiply, if the two vectors were E1 and E2? So this is E1. This is easy, no? What is it? One, is it? Yes. So that's somewhere here. Okay. That's this. This goes to this. What about the second one? E2? Yeah, that will be here. What is the length of E1 and what is the length of A times E1? So this is of length 1, this is of length 1. What is the length of this? It will be of length 1, you can verify. Okay. And this will also be of length 1. Okay. In fact, no matter what vector you take, this matrix will never stretch, well, never scale the vector. It will always be of the same length, at least length measured by the 2 norm. Okay. And what you will find is, so this went here, and this went here, and this angle theta is in fact constant. This matrix will essentially just rotate vectors by a constant amount. Fourth quadrant, is it? Oh, no, then I've done something wrong with the matrix. Let me check. Yeah, it's possible. Yeah, I know what mistake I did. Sorry. I know. Yeah, let's go back to the original example. Yes, now everything is okay. 2, 1, 1 minus 1. That will be somewhere here, roughly. And what is the length of this vector? 2 norm. What is the 2 norm of this vector? What is the 2 norm of the original vector? 2, 1. Root 5. And what is the 2 norm of this? Root 5. Yeah. So the length did not change. What about 1 minus 1? And it's root 2, 0, is it? Yeah. So that's this. And what is the length of this and what is the length of this? Root 2, root 2. So length did not change. In fact, you will find that the length does not change. And the length does not change because why? When does the length of a vector not change when you multiply it by a matrix? What is the property of the matrix that ensures that the 2 norm is the same? If you let's say I have a matrix A, I multiply it by a vector x. The 2 norm of this is always equal to the 2 norm of my original vector. Under what condition? The condition on A. We did this in the tutorial. And A is what? A is an orthogonal matrix. Right? This is an orthogonal matrix. You will verify that A transpose or A transpose A is I. Okay. And in fact, another interesting property is this angle is always the same. No matter what vector you choose, this angle is always the same. In this case, it's 45 degrees. Okay. And these are what are known as rotation matrices. Okay. Rotation matrices are orthogonal matrices, but with one more additional condition, that their determinant should be 1. We've not talked about determinant, but you know how to compute the determinant. The determinant has to be 1. The problem with the previous matrix, it was orthogonal, but the determinant was -1. Determinant 1 simply means that you have a right-handed coordinate system. -1 means you have left-handed coordinate system, if you remember what those are. But otherwise, for pure rotation, you have to have an orthogonal matrix and the determinant has to be 1. Otherwise, you get reflection and rotation, a combination of the two. Okay, all right. So this is an example of a matrix that only rotates. Okay, let's look at the last example. What does this do? Again, we will maybe look at slightly okay, let's look at these two vectors first. What happens to 2, 1 and 1, -1, 1? What is it? For this one? So it will be -1, -2. What about this? Oh, the same. So is it 1 -1 or -1 1? Yeah, it's the same. It's weird. For the first time, we are seeing a process where AX is X. Okay. Okay. This probably is not enough to figure out what is going on. Let's do this. Let's look at another example. Let's look at what happens to E1. What happens to E1? -1, 0. So that goes here. What about E2? Okay. What do you think is going on? No, you were just saying what you're doing algebraically. I'm asking you geometrically what is going on. Huh? Reflected about what? Yeah. 90 degrees, is it? What do you mean by reflected about 90 degrees? Okay, let's say I draw this line. Now can you say what is happening? Yes, if you keep a mirror here, so this will look like this. This will look like this, this will look like this, and anything on the mirror will be on the mirror. Right? So this is an example of a matrix where you are reflecting about this line. Okay, this is pure rotation. This was pure scaling. Here the lengths are all the same. This is pure reflection. Again, you can verify that the determinant here is negative. Okay. And in general, you can have a matrix that can do all of them, right? Yeah. So these three are essentially what the geometric operations that a matrix performs. Sorry. No, reflection is not rotation or scaling. Reflection is a completely different operation. You cannot get the left-handed coordinate system by only doing rotation. If you rotate a right-handed coordinate system, you'll always get a right-handed coordinate system. You have to kind of take it out and do some weird operation like reflection to be able to get a left-handed coordinate system. See, even here it's easy to see. For example, if I take this, right? Okay, this is E1, this is E2. Let's say this is the right-handed coordinate system, right? The left-handed coordinate system would be, there is no rotation you can do to E1, E2. You can only rotate, remember in R2 you can only rotate in the space, right? So you can only do this 360-degree rotation. There is no rotation you can do to this to get this. You can say, okay, I will rotate it like this, but this will be E1, this will be E2. You won't have the other way around. The only way you can get it is through reflection. Is that clear? Yeah, okay. Okay, alright. So, when we were talking about vectors, the representation of a vector in terms of numbers depends on the basis. The representations can be different depending on the basis, but the underlying reality is the same. We are talking about the same point, but it's just because our references are different, our numbers were different. Okay, and if we are talking about matrices, matrices represent linear transformations, and linear transformations in general represent these three geometric operations. Okay, now let's ask this question. We had 2, 1. 2, 1 in the A basis was -12, 3/2. Okay. Because linear transformations represent these geometric operations, and underlying truth is this vector, right? Because a linear transformation, let me not call it A now, because I'm calling it A here. Okay, I'm going to call it B. Okay. Some linear transformation B does these three operations. Okay. Let's find out if you take V, or you apply V to X or XA, because it's doing the same underlying geometric operation, you should get the corresponding vectors out. Okay. Let's so if you take X, right, and apply V, let's assume V is, yeah, let's assume V is this. No. Okay. What do you get? You'll get some Y. What is that Y? X is for now 2, 1. Yeah, 4, 1. Okay. Now, because V does this geometric operation, what I would expect is, if I take XA, right, the representation of the same vector. So, see, all V does is it takes this vector, scales it and rotates it by this amount, right? If I use the representation of X in the standard basis and I multiply it by V, I get this vector. This is 4, 1. Okay. But instead of using the representation of X in the standard basis, let's say I use the representation in the A basis. Okay. It's the same underlying vector. It's this vector, except its representation is different. What will we get if we do VXA? What I would expect to get is YA, where YA is the representation of Y in the A basis. Okay, what do you get? Is that right? Okay. Now, is this YA? I'll call it Y dash for now, or Y cap. Is Y cap equal to YA? What is YA? You tell me what is YA. You'll have to find out. You'll have to find the representation of this in, or sorry, you have to find the representation of this in the A basis. This is why we want to verify if I take, instead of using the representation of X in the standard basis, and performing this linear transformation, I get some vector. If I take the representation of this vector x in the A basis and I perform the same linear transformation, I should get a vector which is essentially the representation of this vector in the A basis, because I started with the representation of the vector in the A basis. Okay. Now tell me if y cap equals inverse y. Okay. If this is equal, then everything is okay. So y cap is ya. What is y? What was a? I can't remember what a was. Was that a? Sorry, the basis that we started with. Is this a? This one? Yeah, okay. Find out what is the representation of y in the A basis. So you have to solve for this. We want to verify if A inverse y equals y cap. Yeah, what do you get? A inverse y. What is the difficulty? What is the problem in solving for? Okay, you should be able to solve A inverse y now. Why is that? But again, why is I just did a whole thing on Gaussian elimination, no? We want to find ya. Ya multiplied by a will give me y. I know y, I know a. I mean, I'll call this ya1, ya2 is 4, 1. Can you please solve this? This is easy to solve, I suppose. Yeah, you tell me. It's okay. We're losing time. Have you solved it? What is it? What is ya? What is it? Half? Five and 3? Okay. So this is what you get. So if you, well, to maybe understand this a little better here, you have this matrix V that represents this geometric operation. Okay. If I input X, right, which is 2, 1 in this case, I get Y, which was 4, 1. Okay. Here I've used the representation of X in the standard basis. What I get out is the representation of Y in the standard basis because I'm getting a bunch of numbers. Okay. Now instead of, let's say I am working in the standard basis, but you're working in the A basis, this basis. Right? So you're saying, okay, I want to do the same operation, but I'm going to use my representation. This representation of X in the A basis, which is minus half 3 by 2, right? Now if I put this through V, or in fact I put this through V, I get something. What I would expect to get here is the representation of Y in the A basis, because I started with the A, my input was in the A basis, so I expect my output to be also in the A basis, right? So what I should get here should simply be Y 4, 1 represented in the A basis. Okay, the representation of Y in the A basis is what? In terms of the matrix A and Y. So XA is A inverse X. So YA would be A inverse Y. Right? So I expect this to be A inverse Y. What is A inverse Y? You said it's this. A inverse Y is this. Y is 4, 1. A inverse Y is 1 by 2, 5, 3. Okay. So YA is 5. Yeah, so this is. So I should get minus 3, 5 into half. What do I get instead? Yeah, guys, okay, here you'll have to listen, please. Yeah. What do I get? What I get instead is this. Minus 1, 3 by 2, which is not equal to this. So there is a problem, right? Even though V represents this geometric operation, if I use the standard basis, I get some result. But if I use the representation of my vector in some other basis, I get some other result and they don't match, right? So that's the problem, right? So it turns out the reason it does not match is matrices represent geometric operations. The geometric operation is the underlying truth. That is what is actually happening. But the moment you assign numbers to represent that geometric operation, you are again basis dependent. Turns out, so your matrices themselves for the same underlying operation will have different representations depending on what basis you are working in, right? So if V represents this geometric operation, let's say in the standard basis, then this thing is correct. Okay, but because now but you cannot use V for the same geometric operation if you are working with numbers from a different basis. You have to find the corresponding representation of the matrix in that basis that you're working in. Okay, so it's not just vectors that are basis dependent. The geometric operation, which is the same, which is the underlying truth, is also basis dependent. Okay, so the V that we've written down here, this is in the standard basis. Okay, so when we took vectors in the standard basis, we got the corresponding output vectors in the standard basis, and that corresponds to this scaling and rotation geometric operation. Right? So if we want to use this V to perform the same geometric operation, the inputs that go in have to be in the standard basis and the outputs that come out will be in the standard basis. So if you want to do this geometric operation using vectors from another basis, the first thing you have to do is convert your original vectors to the standard basis. This will give you an output in the standard basis and you'll have to convert that back to the A basis that you're interested in. Okay. So we can't use, so YA will not be equal to Vxa because V is the representation of the geometric operation in the standard basis. So if we are to use V, right, I'm going to remove this. If we are to use V, right, and V is the representation of this operation in the standard basis, what goes in here should be in the standard basis, what comes out here will be in the standard basis, right? But what I have here is Xa, but Xa is in the A basis. How do I go from the representation of the vector in the A basis to the standard basis? So here, so when you wanted to go from the standard basis to the A basis, you did A inverse. So if you want to go from the A basis to the standard basis, what do you do? Yeah, you simply switch A here. So Y equals A, right? So you take this and you multiply it by A. Now what you get out here after this operation is in the standard basis. Now if you multiply it by V, you're okay. You're doing the correct geometric operation represented by V. Okay? But what comes out is in the standard basis. But what you want is the corresponding representation in the A basis. How do we convert what comes out here into the A basis? Yes, you simply do A inverse and now this will give you Y. Okay? You can verify that. So, in fact there is nothing to verify. So this is here. This is X. Vx produces Y, and if I do A inverse Y, I get Ya. Okay. And now, here, if I look at this whole operation now, I take Xa, convert to standard basis, use the geometric representation of the geometric operation in the standard basis, convert back to the A basis. Okay. But if you look at this, right, this whole thing is a matrix. In fact, interpretation of this matrix is, this is the matrix that represents the same geometric operation but in the A basis. So this is in fact VA. Okay. If V represents some geometric operation in the standard basis, then A inverse VA represents the same geometric operation in a different basis, in the A basis. And whenever you have two matrices A and B, let's say you have a matrix A which is some V times V inverse. Okay. And because I've written V inverse, that means this is square and invertible. Okay. Whenever you have two matrices that are related like this, okay, then A and B are called similar matrices. Okay. And what that means is A and B represent the same geometric operation, it's just they represented in two different bases. Okay. If A represents some geometric operation in the standard basis, the whole standard basis, yes, in the standard basis, what does B represent? What basis? I put it this way, that way. A represents a geometric operation in the standard basis. What basis will B represent the same geometric operation in? Yes, it will be in the V basis, the basis formed by the columns of V. Right? See, the difference between these two is, here V was in the standard basis, VA was in the A basis. I've simply switched the two. So you could have written, so we've written VA equals A inverse VA, or you can write it as V equals A VA n. Okay. If you have the representation of a geometric operation in the standard basis, this is how you get the corresponding representation in the A basis. But if you have it in the A basis, this is how you get it in the standard basis. And VA and V are similar matrices because they represent the same geometric operation. Okay. So now what we've seen is vector representation using numbers is basis dependent. Linear transformations themselves represented by numbers are also basis dependent. Okay. Now we are ready to talk about the main topic of this module, eigenvectors and eigenvalues. Now here, if you look at this particular example, right? If you take this vector, it scales and rotates the vector in the clockwise direction. This one scales and rotates the vector in the counterclockwise direction, right? Now, in fact, what will happen is if I move this vector slightly on this side or this side, right? Because these are linear transformations are continuous operations. If I change this vector slightly, the corresponding geometric operation done by A will also change slightly, right? That means if I move the vector slightly to this side, the new vector that will come out will also be close to the orange line, right? And this vector seems to be, for this vector, A seems to be rotating things in the clockwise direction. Here it seems to be rotating in the counterclockwise direction. So you can argue that there must be a vector somewhere in between these two, either here or here, where there is no rotation. Because at some point it is switching from clockwise rotation to counterclockwise rotation. So there must be a vector somewhere here where no rotation takes place. Okay? And that's essentially the concept of eigenvalues and eigenvectors, where it turns out almost all matrices, and this is only for square matrices, almost all square matrices have vectors such that where A is n cross n, x is Rn, A times x will simply be some scalar lambda multiplied by x. Okay. And this lambda now, we've been avoiding complex numbers so far, but we can't avoid it anymore. This lambda can be a complex number. It need not be a real number. Okay, and we'll see what that means later on. Okay. And almost all, because there are matrices where you can't do this. Okay. But almost all matrices, we'll call them good matrices. Matrices for which this is not true will be called defective matrices. We'll look at them later on. Right. Almost all square matrices will have vectors that satisfy this. That means there are these vectors x such that if you multiply x by A, the resulting vector is simply a scaled version of the original vector. Okay. There is no rotation that takes place. Right. And any vector that does this, that satisfies this, is called an eigenvector. Eigenvector of the matrix A. And the corresponding scalar lambda is called the eigenvalue of A. And in fact, the way you say this is you say lambda is the eigenvalue of A, and x is the eigenvector of A corresponding to the eigenvalue lambda. A corresponding to lambda. Okay, and usually you pair them like this: lambda comma x, where lambda is eigenvalue and x is the eigenvector corresponding to the eigenvalue lambda, and this is called an eigenpair. Okay. I mean, the first time you come across this, it's confusing as hell as to why anybody would bother with something like this. Just take it for granted now that this has some really great applications. Okay, and this word eigen is a German term. It's supposed to mean characteristic or something like that, right? Something inherent, right? Eigen means something inherent. So these eigenvalues and eigenvectors tell you something inherent about this matrix. Okay? So they tell you something deep about the nature of the matrix, and it turns out that's very useful in many applications. Okay, that's why it's important to study this. Okay, and in fact, if you see, if I take the matrix A, right, and let's say X is an eigenvalue with corresponding to the eigenvector with the eigenvalue lambda. What will happen if I take alpha times X and I multiply it by A? Well, what I will get is lambda times alpha times X. Okay. Okay. So in fact, the eigenvalue or the scaling factor is the same, even though the vector is different. It's not X, it's some scaled version of X. So what really matters here is lambda, and this X is not unique. I could have taken 4 times X, minus 3 times X, 35 times X. All of them would be an eigenpair corresponding to this eigenvalue lambda. And another important thing that I forgot to say here is you cannot have, because then it's stupidly true. And there are infinitely many lambdas that will satisfy this, so X cannot be 0. Okay. In fact, if you look at this, right, if you have the eigenvalue lambda and one corresponding eigenvector X, in fact, any vector, so, and this is, let's say, one eigenvector that satisfies this equation. Any vector from the span of this vector will satisfy this. That's essentially what I've written here. Right? All scaled versions of X are in the span of X. Right? So, if you have an eigenvalue lambda, there is an entire one-dimensional subspace, at least one-dimensional subspace that will satisfy this. Okay? And this subspace, one-dimensional, or this subspace that satisfies this property is called the eigenspace of lambda. Okay. Again, these are all definitions that you remember. Okay. Now the question is, okay, you've taken my word that this is something very important. Then the question would be, how do we find out these eigenvalues and eigenvectors? Okay. Lambda x, Ax equals lambda x. So the problem here is we don't know lambda, we don't know x. All we know is A. Okay. If we move this to the left side, I get this, and notice this is a vector. Yeah. And you can write this whole thing. So this is some vector minus some vector, and this vector is A times X. You can write it as A minus lambda times I to X equals 0. You can verify that you can actually write it like this. Okay. So you can write X as I times X. Then you simply take X out. Yeah. And if this is 0, right, what does it say about this matrix? And X is non-zero. You have to go back to your solution of linear equations. You have a matrix multiplied by a non-zero vector that produces 0. So what can you say about A minus lambda I? No, A is not 0. Need not be 0. A can be 0. A need not be 0. Well, correct, but what does it say about the matrix A minus lambda I? If A minus lambda I times X is 0, where X is non-zero, what can we say about the rank of the matrix? Is it a full rank matrix or a rank deficient matrix? Yes, so this means that this matrix has to be rank deficient. Okay. And one way to find this out is whenever you have a rank deficient square matrix, the determinant of that matrix A will be equal to 0. We've not seen what determinants are, but you know how to compute, so let's just assume that this is true. Okay. So if you have a matrix A and lambda is an eigenvalue of the matrix A, then A minus lambda I, the determinant of that has to be 0. Okay. And if you compute this determinant, right, what you will get will be a polynomial. This is polynomial. This is called the characteristic equation or characteristic polynomial, and you equate it to 0, and this is called the characteristic equation. And if you equate it to 0 and find the roots for this polynomial, those will all be your eigenvalues. Okay. If A is n cross n, this will be a nth order polynomial, and an nth order polynomial will always have n roots. It could be complex, but it will always have n roots, right? So any n cross n matrix A, or well, in fact all n cross n matrices A will have n eigenvalues, okay, which are given as the solution to this polynomial equation, where this polynomial equation is nothing but the determinant of A minus lambda I. Yeah, the roots of this polynomial will be the eigenvalues of the matrix A for all matrices, all square matrices. Okay, let's do one example. But let's do one. Okay. So if we want to find the eigenvalue of this, we first form this matrix. What will this be? A minus lambda I. What will that matrix be? It will be 2 minus lambda, 1, 0. Is that okay? And if lambda is an eigenvalue, then the determinant of A minus lambda I is 0. And what is the that's this? What is this? What is the determinant of this? Sorry? Sorry, yes, I'm wrong. Yes, it's 1. Yes. What is the determinant of this? So it will be, this is the symbol for the determinant, equals 0. How do we compute the determinant of this? Yeah, you cross multiply these two minus these two, so it will be 0, so that will be 6 minus 5 lambda okay. Okay, tell me what the roots are. It has 2 roots. Sorry? 5 and minus 1, is it? Are you sure? If you add 5 and minus 1, you get 4. So that's not minus 5. So that's 5 and minus 1 is not the answer. Maybe I should have taken a simpler example, because what about this? Maybe somebody else can try this. Try 2, 2, 1, 1 and tell me what you get. It's complicated. No, if you do that, it's going to get messy. It's fine. Not worth doing on the board. Sorry? Sorry? No, but when you try to compute x, no, it will become messy. It's fine. Maybe you can do this, tell me what the, or you can do this and tell me what the eigenvalues are. Yeah, not worth fighting the arithmetic. So this will be 4 minus 4 lambda plus lambda square minus 1 equals 0. So lambda square minus 4 lambda plus, yeah, this is fine. Okay. What are the roots here? Minus 3 minus 1, right? No, or lambda minus 3, you're right. 0. So the roots will be, those are the two roots. Okay, so those are the two eigenvalues. So for this matrix A, there is some vector x, okay, such that if you multiply that vector by this matrix A, you will get 3 times that vector, and there is another vector x which is not equal to the original vector, such that if you multiply that vector by this matrix, you will get the same vector back. Okay. Now the question is, how do we find the corresponding vector for this lambda? We do the same thing as before. So we know that there is some vector x such that if I multiply by x, I'm going to call it x1, because I'm going to call this lambda 1 and this lambda 2. Okay, the two eigenvalues of the matrix A. So I know, and I'm going to assume x1 is the eigenvector corresponding to lambda 1. So x1 will give me lambda 1 x1. I know what lambda 1 is. Lambda 1 is 3 for me. Right? This means A minus 3i into x1 equals 0. I know lambda. I know this matrix completely. Right? What is this matrix now? So it will be, no, minus 1, 1, 1 minus 1. Multiplied by x1 equals 0. Now can you tell me what is x1? We know this is rank deficient. We now have to figure out the homogeneous solution for x1. Yes, so x1 will be any vector like this, 1, 1. Okay, so that's our first eigenpair, 3, 1, 1. What about the second one? So we have another eigenvalue which is lambda 2. It's 2. Lambda 2 is 1, so implies A minus I into x2 is 0. What is eigenvalue? Eigenvector corresponding to lambda 2. Yeah, have it? Yes. So the second eigenpair is 1, And that's the complete solution for finding out the eigenvalues and eigenvectors of this matrix A. Okay. And in general, n cross n matrix will have n eigenvalues, and if it's a good matrix, then it will have n eigenvectors as well. It turns out the bad matrices will still have n eigenvalues, but they might not have n eigenvectors corresponding to the n eigenvalues. Okay. All right. எடுத்துக்கோ. I'm going to remove this. We'll do two more examples. Yeah? Okay. Let's do the next one. I won't solve it, you guys can solve it and tell me. Okay. First tell me what are the eigenvalues, and then you can tell me what are the eigenvectors corresponding to the eigenvalues. I'll come to that. Yes. Yeah. Bad matrix is you don't have enough number of eigenvectors for all the eigenvalues, and we'll see examples of that. What are the eigenvalues? You have it? Yeah. 2 and 3? Okay. So, your eigenvalues are lambda 1 equals 2. Okay. What are the eigenvectors corresponding to 2? Lambda 1. Yeah. Why will it be? It cannot be, eigenvector cannot be 0. Hey, here eigenvector cannot be 0. Okay. Yeah. Okay, that's your A minus lambda A, right? Yeah, tell me what the eigenvectors are. You know how to solve for the homogeneous solution, so tell me what the homogeneous solutions are and the corresponding eigenvectors. This one? Yeah, what is it? Yeah, good. Okay, what about this? What about the next one? That's correct. So eigenpairs are 2, 1, 0. Oh yeah, 3, in fact, this is a special matrix. The eigenvectors are the standard unit vectors. Is it clear? Okay. All right. Let's do another one. This one. Yeah, yeah. What about the eigenvectors?
We will want the eigenvectors because the eigenvalues are same.
Yeah. You can get two because you can choose anything you want. That's all. Yeah. So what? Yes. That's why I put this problem. So what do we do now? So if that matrix is 0, what can you say about x? Hey, hold on. Why will it have to be 0? No. Hey, sometimes the solution is really dead simple and dumb. You don't have to. Exactly. That's all. X can be anything. You still get 0. Right? So if that is the case, if x can be anything, right, and x is from R2, it's a two-dimensional space. So we can choose any two vectors. We will choose linearly independent vectors. Then they are eigenvectors of this. In fact, here everything is an eigenvector. Okay? But the point is this. Compared to the previous two examples, right, where the eigenvalues were unique, here the eigenvalues were repeated, and you ran into some trouble like this, right? So this idea of defective matrices, right? Whenever we have repeating eigenvalues, we can run into trouble. As long as the eigenvalues are unique, then you can always do this. Whenever you have repeated eigenvalues, then you can potentially run into trouble. Okay? Here we didn't run into trouble because the eigenvalue was repeated twice, the root is repeated twice, and when you go ahead and solve for a minus lambda I into x equals 0, the solution that you get for x is from a two-dimensional subspace or space, right? So the eigenvalue is repeated twice and x is from a two-dimensional space, so you're okay. For defective matrices, later on we'll see eigenvalue is repeated twice, but the solution for x comes from a lower dimensional space, like space dimension 1. Then you run into trouble. Okay? So here we are okay. This is still, you can still find full eigenvalues and full eigenvectors, or you can do a full eigenvalue decomposition for this matrix. Okay? Because I could have written here 1, 1, 3, 2. This is a perfect eigenvalue decomposition for this matrix. Okay? Do one last one and we are done for today. This one. Are you sure? Are you sure? What are the eigenvalues? So yeah, what are the eigenvalues? Yes, yeah. Are you sure? Sorry? No. What is the what is the characteristic polynomial? Minus 1 equals 0? Is it minus or plus? Yeah? So what can we say about lambda? Yes. So what will be the roots? We said we can allow complex numbers, no problem. What are the eigenvalues now? Yes. So minus I. Now solve for, now you do the same thing. Solve for lambda equals I, lambda equals minus I, and tell me what the eigenvectors are. Is it that complex? You have it? See, I think it will be I0 or 0 minus I, something like that. Okay, alright, let's do it. Minus 1, 1, 0, this will be minus I, minus I. So this will be minus I. Sorry? One and I is it? Yeah, you're probably right. So this will be x. 1 minus I, that will give you 0. This will be 1 minus I, which is I square plus I square, which is minus 1. This is okay. This is one of the eigenvectors. And the other one for minus lambda equal minus I, it will be I minus 1, 1 I, x equals 0. So if you have 1 I, this is 0, 1 I, yeah, it's fine. That's the second eigen. So this is the eigenpair is I 1 minus I 1 I. Okay, all right. Just the last point before we proceed. See, remember the example that motivated us to this was this matrix which took this vector here and took this vector here, right? We said here you have clockwise, here you have counterclockwise, so there must be something where some vector where it's 0 rotation. But what if you have, what is what does this matrix do? That A equals 0, minus 1, 1, 0. What geometric operation does it do? Let's figure out by looking at what happens to E1. What happens to E1 if you apply that matrix? This one. Zero, 1. It becomes this. What happens to E2? E2. So this goes here and this one comes down. What happens to minus E1? One zero, is it? If you multiply this by minus E1, what do you get? You'll get, if you take minus, this is minus E1, if you multiply it by this, you'll get this. If you take minus E2 and multiply, you'll get this. So what is this matrix doing? Sir? Yes. It rotates all vectors by 90 degrees. That is the problem, right? Because our definition for eigenvalue, eigenvector was, oh, by the way, there are vectors which are not rotated at all. Okay. Well, that is what this means, right? If I take x, I get lambda times x. That means x's direction is not changed. It's just scaled. Whereas now you have a matrix that always rotates by 90 degrees. That means there is no real vector that undergoes zero rotation. But there are complex vectors that corresponding to this matrix which actually undergoes zero rotation. Because here this matrix always rotates stuff by a constant angle. In fact, you will find that rotation matrices will have complex eigenvalues and complex eigenvectors. Okay, all right. Yeah, that's all. See, okay, the way I understand it is you now have to think of this matrix as a matrix in a, let me phrase it correctly. You have to think of this matrix as something that transforms elements. So this would, we would say, is R2 cross 2, right? Take stuff from R2, project stuff onto R2. But a general way to look at this is to think of this as a C2 cross 2 matrix. Take stuff from C2, which is two-dimensional complex, well, two C's, right? To C2, right? But if you look at C, right, the complex space, you can think of the complex space as R2, because to represent a complex number you need two real numbers, right? And in fact, when we associate a line with R, we associate a plane with C, right? So you can think of C as essentially R2, okay? So this rotation that, okay, if you look at that matrix, no, it looks like pure rotation from R2 to R2. But if you look at it as a generalization of a matrix from C2 to C2, there are vectors which don't get rotated at all. They only get scaled. Okay, that would be how I would view this. So what I'm essentially saying is, this is a generalization of a matrix from a matrix that maps from a four-dimensional set of four real numbers to four real numbers. This is a special case because the imaginary components are all zero in this case. Okay. So in a reduced dimension, it looks like there is no vector that undergoes no rotation, but in fact in a higher dimension there are these vectors that actually undergo no rotation. Okay, all right, that's all. Okay, we'll meet tomorrow then.